The 1930 Nobel Prize in Physics went to this gentleman, Sir Chandrasekhara Venkata Raman, which I'm not going to try to pronounce again. From now on, we're just going to call him Professor Raman. But he won the work for his work in the scattering of light and discovery of an effect named after him. What the heck does that mean? What that means in a little more descriptive terms is that when light comes in and meets particles that are smaller than the light's wavelength, the light spreads in different directions, so it scatters. That's why it's called Raman scattering. This occurs typically when light packets, those photons we've talked about a couple of times, encounter molecules in a gas, or when you take part of the surface off of something and float it into a gas. It's very interesting to work. But in 1928, he discovered this when a small portion of the scattered light acquired other wavelengths than the original light. And that's because some of that incoming photon energy can be transferred to a molecule, and having that molecule get a higher energy level. Remember, we talked about those electrons going from one energy level to another energy level, and then when they cascade back down, they emit different light. But what that does is it allows you to analyze different types of material. When you're working in a science lab, it's very important to understand your exact starting material. So is it pure iron? Is it 99% iron, 95% iron? What are those other constituent pieces? All of that is shockingly important to know, and techniques like Raman scattering help you fully understand that. And from an industrial standpoint, that's also very important, because when you go through an industrial process, say a manufacturing process, have you altered your starting material in some way, or has the finished product not quite exactly what you wanted? Because that can have bizarre and funky consequences. For instance, are you trying to make a corrosive resistant material or a corrosive resistant object? Are you trying to build a lock that doesn't get all rusty so you can't open it? Those are important things to know, what the starting material versus the ending material is as you run it through that industrial process. I know it's kind of boring stuff, but don't worry, this stuff has other applications as well. Now let's dig a little deeper on this one. So Raman scattering itself, the way it works, we discussed a little bit, but it does produce scattered photons with different frequencies depending on the source and the properties of the material it goes through. And what you're really looking at is the vibrational and rotational properties of those scattered molecules. And the rest, it really is a very useful process for chemists and physicists. It analyzes carbon materials, material science and new materials, pharmaceuticals, life sciences, energy technology, art conservation, and cultural heritage, as well as the topic of many favorite TV shows, forensics. So his work was not just for scientists in a lab, it actually has applications all over the place, which is one of the reasons Raman spectroscopy is still a very common tool taught to early year grad students and some later undergraduate students. So I hope you'd enjoyed this one. This one was interesting to me. I've used Raman spectroscopy before, but I never really thought too much about it. I never even, honestly, I was surprised it won not surprised it won the Nobel Prize, but it was news to me. It happened in 1930. I would have assumed it would have been a little bit later, because today this is done in labs with lasers and all kinds of fancy stuff. But early on, when he did this work, this was a much different world to try to do these sorts of things. So I hope you've enjoyed this. Please don't forget to click subscribe and like. It does help us out with the algorithms. Have a great day.